Sigma W is formulated to handle structural elements such as beams and bars. These are essential elements for modeling soil structure interaction. Here's an example that has been set up to illustrate how beams and bars behave. We are going to open up SIG04 in a little bit. This example is workshop example is based on one of our detailed examples that comes with a PDF document where all of the cases have been analyzed and verified with hand calculations. So if you're interested in the verifications for all the different cases in this file, I refer you to the detailed example. In the workshop here, I want to illustrate to you just a few highlights on the features of beams and bars and how they are used and defined in Sigma W. Going then to GeoStudio, we can open up SIG04. And here is the example. Clicking on Key in Analyses, you can see that there are a variety of analyses in this file here. The first one is a simple beam supported at both ends in the vertical direction, supported in the horizontal direction at the left end, with a point load in the middle. The next analysis is simply the same beam but with a uniform load. And before we go any further, the problem has been presented to you without the solution. We have to click on the Solve icon, right-click, select All, and reanalyze all the different cases so that we can look at the results in the results view. First of all then, we have a beam at the top here. If we go to the Draw Mesh Properties and we click on this line, we notice that we have checked this box here, Generate Mesh Along Line. Generate a mesh along the line. This is the way that we discretize a line into elements, and when we have a beam, we need a series of elements along a line. We'll see that in the case of a bar, we do not need to generate a mesh along the line. So this is the way that the line is discretized into elements. Going then to the results view, and we can say View Results Information and click on any one of these points and look at the beam data. We can see that in any particular node that we get the moment and the rotation and the shear force, and this is not that informative for a beam, except to note that many times we do use View Results Information. More importantly, we can draw a graph of the moment distribution in the beam. In this particular case, we're looking at the moment distribution from the left to the right in this beam. And here is the moment distribution, and the maximum shear in a beam like this, not shear, the maximum moment is WL squared divided by 8. In this case, we are applying 100 kilonewtons per meter of beam times a length of 8 meters times 8 squared divided by 8 The 8's cancel out, and we're left with a maximum moment of 800 kilonewton meters. So here's the maximum 800. We can also plot the shear distribution, and we know that the load is 100 kilonewtons per meter times a length of 8. Therefore, there should be 400 shear at both ends with a linear distribution from one end to the next, as it properly should be. So here are some other examples. If we go, for example, the beam on a frame, then now we have a beam here on the left, and we have bars and bars, and we have some cross bracing, and these are bars. If we go back to the define view and we say draw mesh properties, and we click on this line, we notice that we have not generated a mesh along this line. A bar is simply hooked between the end points. So a bar is simply hooked between the two end points. It is basically one element. So this bar is hooked here and is hooked here. Going back to the results view, we can say view results information, and we click on a bar, and we can see the actual force in the bar and the actual stress in the bar and the strain. And obviously in this case it's symmetric, so the two bars should have the same value. If we go to the next analysis, go to analysis number 6 on the lateral load. In this case we are applying a lateral load at the left top end, and you can see how the structural frame has deformed. And if we now go view results information, clicking on this bar, the axial force is 858 kilonewtons compression, and this bar should have tension. Yes, and the negative value indicates tension, 321 kilonewtons of tension. So the main purpose here, just to illustrate that sigma W can handle beams and bars. Beams always need to be discretized into many different elements. Bars are simply hooked at the end points of the bar. Beams must be applied on lines or on region edges. So first of all, you have to draw a line, and then you can apply a beam boundary condition to the line, but the line must be discretized, or we can apply the beam properties to the edge of a region. Going back to the define view, under key in structural beams, we can have as many beams as we wish. We have to define for a beam the Young's modulus of the material, the cross-sectional area, and the moment of inertia. And we also have to say, can the beam withstand tension and compression? And we'll see in the next illustrative example that we will use a beam element to simulate something that cannot tolerate compression, only tension. And this is where you select the option of whether you are allowed both tension and compression, one or the other. The bar is very similar. Key in structural bars, clicking on the bar. Once again, we need to specify the Young's modulus. we need to specify the cross-sectional area of the bar. But notice now here that we can define a preforce. And this will come in handy when we simulate something like an anchor where we want to pre-stress the anchor. This is where we can specify the preforce. So once again, this is a brief example to illustrate that we can handle both structural beams and bars in sigma W, and we use these primarily in soil structure interaction problems. So this brings us to the end then of this short illustrative example on beams and bars.